Hello and welcome to Lesson 26. Today's topic is normal distributions. So yesterday we were talking about the different type of continuous distributions, and now today I want to look at what's been coined or named the normal distribution. So your goal today, you can identify the appropriate time to use and successfully apply normal distributions. So this is key throughout the whole course, this unit is to identify what type of distribution do I have. Is it binomial? Is it geometric? Is it discrete? Is it continuous? And then can I apply the appropriate strategies or things that we've discussed in class and you've practiced with the homework. So if a continuous distribution, this is what we've been talking about in the last lesson, is symmetrical. So I'm no longer worried about any skewing or bimodal. Okay, if it's symmetrical about the mean, it has only one mode, and we talked about this very briefly in the previous lesson. And it takes on that shape, and it only has one hump, and the location of the hump is at the mean. So if that is the case, and that's what we're looking at today specifically, of cases like that, then we have what's called a normal distribution. And this is, we talked about yesterday at the end, it was a uniform distribution, so you had to find the area of a rectangle. The question is, how do you find the area of this shape? Because remember, and this is the part I said is tough to get wrap around your head, area under curve is equal to probability. So yesterday in the uniform distribution example, we had to find the area of the rectangle because we wanted to know the probability. Probability. Okay? So now what happens if it's non-uniform? What happens if it's not a rectangle? Some of you might have been asking yesterday, and that's what we're looking at today. So normal distribution characteristics. So I'll give myself another normal curve here. And the characteristics are listed to your right. So the first one, the area under the curve is 1 square unit. Okay? So the area, my green here, is equal to 1 unit squared. Maybe I'll just proper 1 square unit. Okay, so the area under that entire curve is equal to 1. All right, very, very important. Second one, the curve is symmetrical about the mean. So we talked about the location of the hump matches up with the location of the mean. The third one, the ends of the curve never touch the x-axis. So here I am drawing them touching, but in reality, they never really touch. So they get very, very, very close, but they never actually touch. Okay? They're asymptotic. Okay? Now, here's where standard deviation comes in from the previous unit. Okay? Approximately 68% of the data is within 1 standard deviation. So that's to say that if this is the mean, and we move over 1 standard deviation in either direction, the area under here is 0.68 or 68%. Okay? So 1 standard deviation would include 68% of the data. If I went out 2 standard deviations, so I go out that same measurable distance, so remember you came up with a numeric value in each case, so 2 standard deviations, the area in that region would be 95% of the data, or probability of 95%. And then if you go out 1 more to 3 standard deviations in either direction, okay, you're now pretty much including all the data, 99.7% of the data. So we always reference standard deviations because it's something we're able to calculate, and we have a chart that ties standard deviation in for us. So some of the terminology you need to remember is for a mean, we have x bar, and if it's population, it's mu. Remember, they mean the same thing in terms of you're calculating a mean here, but they indicate, are we dealing with a sample or a population? Similarly, standard deviation, S or sigma, means the exact same thing. They both mean standard deviation. It's just so that the writer doesn't have to say, oh, I have a sample, or oh, I have a population. All right, so there's some of the characteristics. So let's talk about the Z-score table. So attached in this on the website, you can find download of this PDF. It is the Z-score table. Now, if you look at this, it has a whole bunch of numbers. So I'm going to try to help you interpret how these numbers work. Okay, so I'm going to take a picture of it just so it's easier for me to reference here. So I'm just going to take that area there. So you want to have this printed out in front of you because you're going to be using it quite a bit and you need it for the test and everything else. So right here, the Z, this column here, is your Z score to 1 decimal. And remember that how do you calculate your standard deviation? So your S is your X minus X bar over your standard deviation. Oops, sorry. Z score, my fault. Or your Z score equals the X minus mean, which would be mu for population. So that's how we're calculating these Z scores. So Z score to 1 decimal place, and then across the top, this is your Z score to the 2nd decimal. All right, so let me explain that further. What you're going to be doing is, if I want to read this particular value here, so I'm just going to circle this one, even though they're all kind of the same at this point. Okay, 0.00008. So that's a probability because this is an area which equals probability. So all the numbers inside this Z-score table in here are areas or probabilities. What's the Z-score for this one? My Z-score would equal, looking over here at the first column, I would have negative 3.1 would be my Z-score. And as I move across to get the exact value, this would become the second value, so negative 3.15. Okay, so the Z-score ties or links us to an area. Okay, it's linking us to an area, and that area corresponds to a particular probability. So when we look at the Z-score, and I go back to the normal curve for a second here, so back up here, what we're looking for is, if I give us a Z-score value, the corresponding graph then, or chart, will tell us the area under this curve. And the Z-score table always measures the area from the point given all the way back to the origin. Okay, so that 0.0008 was probably down here somewhere, so we had this area right here because it's negative 3.15. The negative indicates that you're left of the mean, so I'll just put that in here. So if Z-score is, if it's negative, you're on the left side of mean. And if it's a positive, you're on the right side. Okay. So then, if I want to go back to the Z-score table for a second, what we're going to be doing, we'll be calculating a value, a Z-score value. So, let's see if I can write on here. If I calculate my Z-score to be, let's go with 0.56. That means that I need to find 0.5 on my chart. So looking down the Z-score table, here's my 0.5. The second decimal comes from across the top. So I need to find where it's 0.06. Here's my 0.06. We then come across to find where they meet. And here is my corresponding answer. So if I ended up with the probability of Z being less than 0.56, the probability would be this answer right here, 0.7123, or 71% chance of happening. All right, and do one more because if you can understand the chart, then the rest of it becomes a lot easier. So let's say in this case now, my z-score that I calculated, and I'll show you how to calculate that in 1 second. So it's 1.43. So the question is, what's the probability that the z-score will be less than 1.43? And if people are asking what happens if it's greater than, I'll get to that in a second. So first step, identify the first two decimals, or the first two parts here. So 1.4. So you look down the chart to find 1.4. Identify the second decimal place, which is 0.03. So it's this one right here. So again, you scroll across or look down, and you find there it is there. So we find that probability of our z-score being less than 1.43 is 0.9236, or a 92% chance. Okay, so that's how we're going to use this score. So now I've shown you how to read the chart. Now we're going to go from reading the chart to how do you get the number in order to read the chart. So we'll do that in the next step.